Gina Tourassi, I hope you're on the line now.
Good to see you.
Logo Frontier behind you. You're from Oak Ridge National Lab, and you're personally responsible for the Frontier system in the US, which was announced with a massive splash at ISC 2022 as the machine to get to the exascale. And it's super that you're able to come now and tell us a little bit more about the machine. I'm sure there's lots of interest here.
Thank you so much for the opportunity to share with you the latest news on the very exciting addition to the Oak Ridge Leadership Computing Facility. As you may have heard, that in late May, our team at the Oak Ridge National Lab, in partnership with HPE and AMD, we broke the exascale barrier with Frontier, and we're very proud to have in our facility the fastest supercomputer in the world and the first one to exceed the quintillion floating point operations per second. So here are some of the slides that have been going around and we're posting in different media. The top 500 list listed as first with 1.102 exaflops of performance, which makes this system faster than the next 7 systems combined on the top 500, and that includes, of course, the flagship system in OLCF until a few weeks ago, which is Summit. The system is also more powerful than the next 68 systems combined after that, and more powerful than the next 393 systems combined after that. So this is extremely exciting for us, for the open scientific community, to be considering about how we can leverage this immense computing power to advance scientific discovery across different domains, but clearly biology over the past few years has emerged as one of the top application domains where both high-performance computing at this scale, as well as artificial intelligence, and often interleaving the two, are a very important enabler. The number that we posted, the one that we documented, the 1.1 exaflops for performance, this is the first one, and we really hope that in the next round we will be able to push this performance even further. In terms of the vital statistics of this system is composed of 74 HPE Cray cabinets. Each one of those cabinets weighs 8,000 pounds, so it has been a very interesting exercise to have the system delivered and installed here. It is a hybrid architecture, just like our previous system, in CPU-GPU architecture composed of 9,000 plus AMD EPYC CPUs, and for every CPU, 4 AMD GPUs. The storage capacity is at 700 petabytes, and of course, the networking fabric with HP Slingshot. Something that I need also to point out, we always focus on the LINPACK benchmark, for which, of course, we got the 1.1 exaflops. It is also noteworthy that the system achieved both the #1 and #2 place on the Green 500 list. The #1 place for its energy efficiency on a single cabinet, the TDS cabinet on the system, which is at 64 gigaflops per watt, and the #2 place for the power efficiency on the full system at 52.2 gigaflops per watt. Last but not least, the system demonstrated an impressive performance for the HPL AI benchmark at 6.9, almost 6.9 exaflops on this benchmark. So we're very excited about all the applications we expect to see as soon as the system turns operational. So this system is part of the long history that the Oak Ridge Leadership Computing Facility has since its inception in 2004 in terms of systematically delivering leadership class systems, always on scope, on budget, and within schedule. We started with the Cray system, Phoenix, back in 2004, which was an 18 teraflop machine. And we are now to Frontier. When I joined the lab, it was in 2011. That was still the Jaguar era, a 2.8, 2.5 petaflop system. And within the first year I was here, we transitioned, we decommissioned Jaguar, and Titan hit the ground. So for me, it has been very exciting and humbling experience to be honest, seeing the evolution of the technology, how within a 10, 12-year span, we went from a system that was 2.5 petaflops to a system that is at peak performance expected to be 2 exaflops. So we have seen a steady progress of 10 times per generation. And this is truly, truly impressive. Of course, the past few years have been quite challenging because the big part of the system being developed and delivered has happened throughout a pandemic. We were prepared over the past 3 years for Frontier's arrival in terms of upgrading our facilities' power and cooling capabilities. And we built a new energy plant that can accommodate the system at 29 megawatts of power, as well as accommodate an expansion of the system. This is actually a picture from the first few days in late August, beginning of September, when the system was delivered here. This is one of the first cabinets. This is one of these 8,000-pound beasts that I mentioned, and pretty much right now the floor is filled with the, oops, sorry, clicked the wrong thing. It's filled with these cabinets. So our investment in high-performance computing is critical to our ability to deliver for ORNL's mission and for the U.S. Department of Energy mission. And now that Frontier has arrived, now we are ready to prepare the scientific community to take advantage of this infrastructure for a large range of applications, not only supporting traditional modeling and simulation, which is the traditional type of HPC workloads, but also for large-scale computing and data analytics, as well as for advancing artificial intelligence. Here is how the system looks like. Our early performance on the top 500 is just a preview of the overall capability. So, of course, now that the system is delivered, now that we demonstrated its abilities with the top 500 benchmarks, the next step, of course, is to proceed with acceptance of the system. And this is exactly where we are right now. We are in the midst of acceptance so that we can officially deem the system ready to turn into an operational system. During the acceptance phase, we work with a few selected teams and different codes to ensure that the system is stable to support the large number of users. And I can show you, I'm showing here some preliminary results in terms of working with different kinds of codes that have been part of the early science applications and the car applications that we typically use to kick the tires of this system and stretch it and make sure that we are comfortable for it to become an operational system. One of the codes that we recently demonstrated that it can achieve 2.36 exaops mixed precision operations. This is the COMET bioinformatics code that a few years ago in 2018 was a Gordon Bell winner. And this is a bioinformatics application in the comparative genomics space. We also have tested the system with a neural network application in the climate space for detecting extreme weather patterns. And that for low precision calculations, it has sustained a throughput of 1 exaop. So all of these are extremely encouraging results, and we continue working with different types of code. In the end of July, we start anticipating some of the exascale computing project teams coming in to test with their own codes, and the anticipated deadline for completing the acceptance of the system is end of September, beginning of October. Our goal remains the same, our timeline, the one that we have shared with our sponsor and with the scientific community, is that we will turn the system operational with the beginning of the new calendar year, January 2023. So for those users who are familiar with the different allocation programs that we have, you may have noticed that with the call, the inside call that closed a few days ago, Frontier was one of the systems that our user community could request for their runs. I would like to spend a few minutes, if you don't mind, emphasizing the energy efficiency of the system. The Frontier is the culmination of a long project and an investment from the Department of Energy in exascale computing. Back in 2009, when the Exascale Computing Initiative launched within the Department of Energy, one of the biggest concerns in terms of delivering the exascale system based on understanding the hardware at the time is that the exascale computing capability will come at the cost of approximately, estimated at the time, 1 gigawatt in terms of energy. And of course, this was not a feasible expectation. At the time, a grand challenge was set that the target for 1 exaflop system would be approximately 20 megawatts. And we are very excited to say that we're exactly at that level with the Frontier system. Clearly, the hybrid architectures, the CPU, GPU architectures helped tremendously in terms of boosting computational power, but also keeping the carbon footprint far more manageable. And you can see the changes and the trend from the Jaguar supercomputer back in 2009, which was operating at 3,000 megawatts per exaflop in terms of calculations, to Frontier, which is at 20 megawatts per exaflop. So this is a fantastic improvement in energy efficiency, because of all the hardware advances that have happened throughout this time. This is actually the one comparison that blows my mind every time I show this slide. This is the slide that compares the Titan system in 2011 versus the Frontier system right now. So one cabinet of Frontier, remember we have 74 cabinets, one cabinet of Frontier has a 10% higher HPL than all of Titan, and also it shows you what it means in terms of energy efficiency. This is exactly the kind of acceleration we have achieved as a scientific community, and that is the biggest challenge for the domain scientists, for individuals like me, for example, in the biomedical space. This acceleration of computing begs the question for us to think not only what is the problem we would like to solve, but if computing, based on what computing we have available, but let's reverse the question and say, what problem would you like to solve if computing were not a constraint? So this is the kind of paradigm shift that these kind of technologies, the new systems, are forcing us to do. And when these changes happen within the span of a decade, this is truly a paradigm shift for application scientists that is fairly uncomfortable, because we always tend to think within the capabilities that we have available and the resources we have available. In terms of the different application domains, we expect, of course, Frontier to enable scientific discoveries across all of these applications, but we certainly will start working in late July within the ECP, the Exascale Computing Project portfolio, which clearly has a very diverse range of applications from chemistry, from material science, from climate, astrophysics, as well as from biology and biomedicine. Biology with the bioinformatics, comparative genomics application that I talked about. And of course, there is an application very close to my heart, and that is the CANDLE project, which is a project that is co-led by multiple national labs on the development and deployment of deep learning solutions to enable cancer research. And in this particular case, I'm emphasizing the side of cancer surveillance as a different beast in terms of an application, because it is a truly biomedical application and more on the clinical informatics side of things rather than a biological application, which is more typically an HPC type of problem.
Gina, you have 5 more minutes, okay?
I will go through that. So these are the different scientific highlights that we created over the past. This is a very small sample of scientific highlights from the Oak Ridge Leadership Computing Facility in the past year, but they also illustrate different domains that we expect to see even more activity as we're moving forward. Clearly, with the pandemic, we have supported a large number of applications that are on drug discovery and large-scale screening of small molecules. Some of the threads that the previous speaker talked about. We're seeing applications that are related to large-scale image analytics for cancer detection, but also, of course, we see applications in quantum materials, superconductivity, and so on. Within the COVID space, and in particular with the new initiative that is launching within the Department of Energy on biopreparedness, which means, just like Austin described earlier, what kind of capabilities we need to put into place so that we are better prepared for the next pandemic. We certainly want to support even more of those applications that are all about understanding protein structure, replicating enzyme functions, understanding the membrane channels, protein folding, and of course there is quite a bit of interest in the area of biofuels and biomanufacturing. And of course, that is not going to come to the expense of what we're trying to do in the broader biomedical space. And again, I would like to highlight that by biomedical, I mean very broadly biological as well as biomedical applications. So these are some of the growing areas. We see a lot more activity in terms of proposals that we receive in synthetic biology, bioimaging, digital twins, and of course, precision medicine and precision oncology. All of these threads have a very strong big data component and also big multimodal data component, which poses some interesting challenges for these applications we support. Another activity that's taking place within the Department of Energy is how to better integrate our leadership computing facilities and our computing facilities such as ALCF, OLCF, NERSC with the experimental facilities that are very important part of our research ecosystem. So a lot of use cases are generated to support these kind of activities, and we are working along those lines to enable our researchers make the most of the resources that exist within the Office of Science. Within the Oak Ridge National Lab, we are connecting the Oak Ridge Leadership Computing Facility with our experimental facilities such as the spallation neutron source, the nanophase materials, advanced manufacturing. So we're very much interested in collaborations for development of use cases across these specific vignettes that I highlighted. I would like to emphasize one area that's, again, very close to my heart, and it speaks very much to the biomedical side of things. Most of the biomedical discoveries with tremendous clinical translational value happen at the intersection of domains, and often the intersection of domains requires integration of data that comes from different facilities and different agencies, often different agencies. We can have data that come from instruments, large-scale instruments, think about the cryo-EM facility, and often integrating with data that comes from observational facilities such as different clinical centers, which often involve sensitive or proprietary data. For this type of activity, it's important for leadership computing facilities such as ours to be able to support the workflows that involve these cross-facilities and also cross-agencies workflows. So something that we're working on is how we can support our PIs in terms of pursuing projects that require federated learning with privacy preservation. This is exactly what's happening right now with the DOE, with the partnership we have between the Department of Energy and the National Cancer Institute and the CANDLE, the exascale CANDLE project that I mentioned earlier in cancer surveillance. This is a project we're developing large-scale language models to support the National Cancer Surveillance Program in terms of collecting and aggregating clinical information that they can extract from different data sources to populate the National Cancer Registry. The information comes from different registries, which, because of how the system is set up within the US, they cannot share data with one another. So through a federated learning and privacy preserving framework, we want to be able to enable these entities to leverage the supercomputer and jointly trained models, taking advantage of each other's knowledge base without really sharing data with one another. So this is something that we're working on Summit, and the plan is to transition that to Frontier as soon as Frontier becomes operational. For those of you who don't know, already Summit supports proposals that are coming with proprietary and sensitive data through a capability which we call a Citadel, the Citadel capability, which is a workflow for scalable analysis for protected data. So when you apply for an allocation through Insight, ALCC, or the division director's discretionary vehicle, it doesn't matter, you can list there that this particular project, your application, involves sensitive data, and then we provide allocation according to this new infrastructure, the scalable protected infrastructure, which is part of the Summit system. And this capability has been operational for a year now, under the authority to operate. We are the only leadership computing facility within the Office of Science that can support projects that have PHI, PII data, or proprietary data, such as engagement with different, with industry. So I want to remind everyone that we are a resource open to the scientific community. These are the different allocation programs that we support inside, where 60% of our cycles go to the inside allocation program. Another 20% goes to ALCC. The difference between the Insight and the ALCC projects are Insight projects are for the grand challenges that require the very high level of computing, and they require at least 20% of the system to be able to deliver what they need to deliver from a scientific perspective, where the ALCC allocation is an allocation that is more targeted to strategic partnerships and to very timely scientific challenges. For example, OLCF has been supporting the HPC consortium by allocating cycles for COVID-related applications through our ALCC allocation. Of course, there is a certain allocation for the ECP teams, and the remaining 10% is the director's discretionary program, which is an opportunity for new users to become familiar with our system and our processes, and this DD allocation is open throughout the year. And with this, I would like to highlight again the resources that are mentioned in this talk. You can find more information about OLCF on our website and about the two primary allocation programs, InSight and ALCC. You can find about DD on our main site at OLCF. And with this,
thank you very much.
Thank you.